Welcome to the Journey Shake Cam. Please do the 2 warm-up questions to the best of your ability and we will discuss them in a moment. In number 1, we are using the BronstedLaurie theory of acids and bases. And in BronstedLaurie, we say that hydrogen ions are protons, and an acid is a proton donor, and the particle remaining after it donates the hydrogen is the conjugate base. The base is the proton acceptor, and the conjugate acid is the particle obtained after the particle accepts that hydrogen. And therefore, when we look here and then we look here, we see that it picked up a hydrogen, and that would make it the base. And wherever it is with that hydrogen is my conjugate acid. Then if I look at the other compound, I see here and here it has lost a hydrogen, and that would make it the acid. And wherever it is without that hydrogen is my conjugate base. In the second one, we have hydrosulfuric acid. And when I look at it over here, it has lost a hydrogen, and therefore it is an acid. And the particle without that hydrogen is my conjugate base. Then the ammonia picks up hydrogen, therefore it is acting as a base. And this would be my conjugate acid. And BronstedLaurie's theory is always with conjugate pairs. There are an acid with a conjugate base, a base with a conjugate acid. And we look for the hydrogen. Where does the hydrogen go? Which one gets a hydrogen? Which one gives a hydrogen? And that's what you have to look for. And that's how you do number 1. In number 2, we must first draw a dot diagram, and then we are going to decide if the compound or the element is a Lewis acid or a Lewis base. A Lewis acid is an electron pair acceptor, and electrons have the opposite charge of a proton, and therefore a BronstedLaurie acid is a proton donor. So we're talking about 2 different things there. Well, when we draw the dot diagram for ammonia, we see that nitrogen has 5 dots. It's an S2P3 electron configuration. And I have my 5 dots for the nitrogen, and hydrogen has 1 electron for each hydrogen. And therefore, there's no room here to accept an electron pair. And therefore, it must be a Lewis base. In the case of boron trifluoride, there is a space here where an electron pair could come in. It has an opening for an electron pair, and therefore it acts as a Lewis acid. And when we discussed Lewis acids and Lewis bases, we had these 2 compounds, and they actually combine together so that this electron pair then shares with the boron and combines in a reaction. Now, carbon dioxide forms a very interesting molecule. Carbon has 4 electrons in its valence electrons, and each oxygen has 6. So we end up with a double bonded carbon. And it looks like a space for electrons to come in, and we can do that because if we break that double bond, then we can add another atom, and therefore this acts as a Lewis acid and could potentially form the carbonate ion or the bicarbonate ion. Then the fluoride ion fluorine has 7 dots, S2P5. It gained 1, which I show as my negative charge here. There's no room to add more electrons, and therefore it must behave as a Lewis base. And that's number 2. And then you have a review worksheet that you will be working on for tomorrow. And after that, we'll have the assessment. And we're getting close, and you've had lots of practice. And I know that you'll do well on that. So you just do that review worksheet. That will give you an idea of what to expect. And I can't wait to see you tomorrow. Bye!